Hi everyone, we are back and we are on our last problem set. So let's go ahead and work through this. So let's look at problem number 1. So we need to identify on this stress strain curve, and this is not the dark blue line, this is D. So indicate where and mathematically how I can find the Young's modulus, UTS, sigma y, blah, 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 for our curve D. So we know that basically this is going to be my strain and failure equals about 130%. Here I'm going to say that this is pretty much my yield strain, which is 10%. I'm going to say that the slope here, the slope basically right here, I'm just going to take this kind of first, let's just say I take this first kind of point here. Actually, I'll do here. This looks to be like 5, and then this looks to be about, this is 10. So my slope is my Young's modulus. It would be the rise. So essentially from 0 to, let's say 2.5 MPa divided by, and that looks to be about, let's see, if that's 10, like 2 point, let's just say 2 point, that's 2.5% strain divided by 0.025 strain. So that would be my Young's modulus, then we could calculate that out. So got my Young's modulus, my UTS would be right here as well. So it's the largest kind of strain value. So this is my sigma y, this is also my sigma f. Considering, or if we consider that this is the breaking point here, so that's equal to about, let's say about 8 MPa. Got that. Elastic strain energy, we would just take the area under this kind of section here, the elastic regime. So, and we take, basically, to calculate the elastic ESE, it's going to be equal to the volume times 0 to sigma y of stress dE. That's it. And the same thing for toughness. Toughness would be the entire area of the curve to the volume. So same equation for toughness, except we would just switch essentially to this, strain and failure. Great. So now we need to kind of figure out what regime do dislocations start to move. That is the plastic regime, regime 2. Do dislocations exist in elastic regime? Yes, they do, but they don't move, and we are not initiating or creating dislocations. So which material corresponds to what mechanical description below? And explain your answer. So what is the stiffest material? So again, stiffest means the largest Young's modulus. So if I'm looking for the stiffest material, it's the largest Young's modulus, and that is going to be A, as we can see here, because the slope here is larger than these other slopes in that linear, the first linear regime. So that is going to be A. Toughest, I cannot answer this question because I don't know the volume of my material, but it would probably be either D, or it would probably be, or actually, excuse me, not D. The toughest material is, again, the total area under that curve. So I would say, and possible answers are probably A or D, again, depending on the volume. So A or D, because again, total area under the curve. Strongest, in terms of UTS, that is going to be A. Highest yield strength, also A. So you can see here again, this is where we're deviating from linearity, deviating sigma y, so A is the winner. What has the largest, or what is the most ductile? That's a combination between C and D, because again, we don't really see them necessarily breaking at all. So C and D. The most brittle, by far, is A, because we're fracturing here. So that is number 1 done. Now, let's get into our Mohr circle. So determine the principal normal stresses and angles for all 3 planes, for the stress straight below, and write out the stress straight for a counterclockwise rotation of 37 degrees, all 3 planes. So I need to look at and draw a Mohr circle for the 1, 2, I need it for the 2, 3, and I need it for the 1, 3. 1, 1, 1, 1. So let's draw out the Mohr circle in the 1, 2 plane. So 1, 2, so I've got my tau, normal stresses. So I've got here 29, I've got here 0, and I am already in the principal stress state. So my principal normal stresses are sigma 1 equals 29 megapascals. My sigma 2 is equal to 0. I could do something very, very similar for the 1, 3 plane. So 3 tau, tau and stress. So now I have minus 27 and 0. And again, I am in the principal stress state, so I am in my principal stresses, so my sigma 1 is 0, my sigma 2 is equal to minus 27. And if I want to figure out what is the stress state for, basically the stress state in each of those planes for counterclockwise rotation of 37 degrees, counterclockwise is positive, I know that. So I can actually go ahead and start to kind of do this problem. Let me kind of change the dimensions here of this guy so we can kind of see on the plane. So I'm going to define, again, my kind of vector. So my stress 1, 2 is equal to normal stress, shear stress. My stress 2, 3 is equal to, again, normal stress, shear stress. And then finally, my stress 1, 3 is equal to normal stress, shear stress. So, if I were to rotate, or if I want to get the stress state of, my 1, 2 plane 37 degrees counterclockwise, which is positive, T dot stress 1, 2 slash dot, basically theta goes to 37. And then backslash n, and voila, there we go. So that would be my stress state. And I can do the exact same thing for the stress 2, 3 plane. Voila, I've got it. So, what are we going to do for so again, we determine essentially the principal normal stresses for, and all angles for this, which is this occurs. So again, we're already in the principal stress state, so we need a rotation to get there of 0 degrees here. But the hard question is my, sorry, I switched colors there. So this should be blue. So, actually, this is not 1, 3, excuse me. So, apologies for this. We'll make sure, we'll adjust it right now. This is the 2, 3 plane. Got ahead of myself. So the 2, 3 is this. Same curve, so tau here, again, minus 27, 0. Here I'm lying on that principal stress state, so what's the theta? Is equal to 0 degrees. Theta here, again, to get to the principal stresses. And then again, my sigma 1 will be 0, my sigma 2 will be minus 27 MPa. Now, let's take a look at our 1, 3, our real 1, 3 plane. So if I look at tau 1, 3, tau, and sigma, I got a little bit of a different situation because I am not in my principal stress state because I have shear stresses. So I'm going to have at 51, I have here 29, here 27, and then this is going to be 51, 51. So I have 4 coordinates at here, 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 and here. And my circle goes through them, but I don't know my principal stress state, but I can figure that out and figure out what's the 2 theta angle here. So we've seen this in class. We've done this quite a few times, essentially, on our YouTube channel. I think there's like 4 hours and many example problems. But I can solve for the angle where I am in my principal stress state in the 2, 3, in the 1, 3, because I can just solve for what theta will allow me to get rid of that shear stress. So if I look at stress 1, 3, you see I have 3 equations here essentially. So this is my 3rd equation to get me my shear stress. So I need to solve for when does this 3rd equation, what value of theta will this be equal to 0? So 3, set this, and then solve. When does this equation equal 0 in terms of theta? And let's solve for this numerically. And when we do that, we see, pull out the smallest one here. So let's pull out this value, and it's just going to be at an angle of minus 30. So, and you could do this, again, you get 4 values because of circular symmetry. Actually, let's pull up. Actually, let's use the, exactly, right here. So, that's my angle here. So that will give me, if I plug that in, so let's go ahead and do that. So T dot stress 1, 3 slash dot theta goes to minus 30. And you see our shear stress is 0. And again, we get our kind of normal stresses. And if we put the whole stress state, so 29, 0, minus 51, and then 0, 0, 0. And if we did minus 51, 0, 0, minus 27. So if I did eigenvalues of stress, let's look at these. So these would be my 3 principal stresses. So we get that from here. So we see that this is our, so this is my sigma 1 for 1, 3. So it's 59 something. So let's go ahead and check that out. So, yeah, actually, let me make sure. Minus 51, yeah, exactly. So I get something along the lines of 559.1, and my sigma 2 is minus 57. So to draw my 3D Mohr circle stress state, and again, I could do, okay, well, what's the stress state for 1, 3 at minus 37, or at plus 37, excuse me, clockwise rotation, would just be this. So you can give those values, again, for these rotations, pretty straightforward using this approach. Now, we've drawn the Mohr circle, and then now we need to figure out, again, the principal normal stresses, and then, we also need to give the maximum shear stress values. So shear stress, to get that rotation, we would just do, for example, when we're in the principal normal stress state, we just need to go to basically 45-degree rotation. So remember, 90 in Mohr circle, but remember we're in 2 theta space, so 2 theta equals 90, so in real space 45. And so for here, my maximum shear stress value, my tau max, will just be equal to sigma 1 minus sigma 2 divided by 2. And this holds for all of these different planes. So that's, so just be, here it'd be minus 27 divided by 2. So 27 divided by 2, 29 divided by 2, and then 59 minus 1 minus 57. So that's going to be a pretty large value, but you get the picture essentially. So it's just going to be the radius of our circle. So that will give us the maximum shear stress values. So we could do that quantitatively if we want. So let's go ahead and let's do 59 minus that. Actually, just do plus. And then divide that whole thing by 2. 29 divided by 2, and then look at that numerically. So these are my maximum shear stress values, 27 divided by 2. So again, just the radius of our Mohr circle. That's it. Now, if we were to draw the full 3D Mohr circle, what we would do is we'd look for first, what is our maximum sigma 1 value? Well, that'd be my 59. So if I wanted to draw the full 3D Mohr circle, oops, my pen is not responding right now. But if I wanted to draw the full 3D Mohr circle, all I would do is look at what is my maximum for all of these 3, 1, 2 planes. What is my maximum sigma 1 value? And that's going to be my sigma 1. What is my maximum sigma 2 value? That's going to be my sigma 2. And what's my minimum sigma 2 value? And that's going to be my sigma 3. And that's going to help us solve essentially the problems below. So my maximum sigma 1 in this problem, sigma 1 is equal to 59.1. My maximum sigma 2, let's look at it. Negative, 0, and negative. So that's going to be 0. And my sigma 3 is going to be equal to my lowest, minus 57, 0, minus 27. So that minus 57, something value. So, and you could kind of draw that Mohr circle as we've kind of done previously. So my Mohr circle, let's draw that right here for 3D. So I've got my sigma 1, I've got my sigma 2, and I've got my sigma 3. Draw a circle like this, draw a circle like this, draw a circle connecting them. So my maximum in the entire stress state for tau is just going to be my sigma 1 minus sigma 3 divided by 2. That's it. So very similar. Again, lots of good circle geometry. We can give you those quantitative values, and that's fantastic. All right. So now the question is asking us the above material, and actually let's go ahead and define those. So I'm going to say that this is going to be my sig 1 equals this, my sig 2 equals 0, and my sig 3 equals. And again, linear algebra, eigenvalues, doing it, geometrically, plug and chug, they all give us the same answer. So sigma 1, sigma 2, sigma 3. Now, we are told that this material should exhibit a yield strength of 100 megapascals. So my sig y should be equal to 100 times 10 to the 6. So, will it yield via the von Mises-Tresca ranking criteria? So ranking is sigma 1 greater than sig y. No, so it's not going to yield. Is my my Tresca criteria is sig 1 minus sig 3. Is that greater than sig y? No. Is, now I need to go back to my, let's go into our notes. Let's go into lecture 7. Where are you, lecture 7? Ooh, where is that? Here, let's go to lecture 7 here. And let's go to our yielding, because this is an equation that's not super easy to remember. So my von Mises Vm equals, so let's do square root of 1/2 times sig1 minus sig2 squared plus sig2 minus sig3 squared plus sig3 minus sig1 square root. So is Vm, oh shoot, sorry, excuse me. We made a little bit of mistake, not a little bit of mistake. We need to make sure to look at this in terms of, these are all MPAs, excuse me. So these are megapascals. So remember, we're working this problem all in megapascals, so we could have just kept this at 100, but answers are still the same. But now we see that the Tresca criteria, apologies for that error, but the Tresca criteria changes, and now, if I look at my Vm, is Vm greater than sig y? Yes, so we will yield not via the Rankine, but via Tresca and von Mises. Excellent. So that is a couple problems down. So let's look at Pset 4. So that's 2, 3, and 4 all done. Now let's look at the next problem. A capsid, which in case of virus must withstand the pressure of tightly folded DNA and osmotic pressure. We have a capsid that is actually, and a capsid is just basically this cylindrical. It's like a virus wall. So not like the COVID-19 viruses, this is drawn basically spherically. We have a capsid. I'm going to draw my coordinate system 1 and 2. It is 10 angstroms thick. So my thickness is equal to T equals 10 times 10 to the minus 10. My radius is equal to 30 times 10 to the minus 9. So my R divided by T is 30, so it is a thin wall pressure vessel, so I know then that the one direction is longitudinal, so I could go ahead and write out sigma L, sigma H, 0, 0, 0, 0, 0, 0, 0. I know that my sigma H is equal to delta P R over T. I know that sigma L is equal to sigma H over 2. I know that my E sub H equals 1 over E times sigma H minus nu times sigma L. And I know that my, let's go ahead and place these things here. I know that my epsilon L is equal to 1 over E times sigma L minus nu sigma H. So we've got those values, so now we can go ahead and start to solve the problem. And we know this is a virus, so I could treat it like a polymer. Nu is equal to 0.4. My Young's modulus is a gigapascal. And then now we can go ahead and figure out. So what is the total pressure difference across the typical, and it says that it can withstand a normal strain of 2% before lysing. So I know sig H equals del P times R divided by T. Sig H equals sig L, excuse me. Sig L equals sig H divided by 2. I know that my EH equals 1 divided by Y times sig H minus nu times sig L. And EL equals 1 divided by Y times sig L minus nu times sig H. So we can see here that when it says it can endure a normal strain before lysing, the largest strain will always be our EH, our hoop strain, essentially. So I'm going to solve for delta P when this is equal to 2%, so 0.02. So solve gives me del P. So this is my pressure. Once I have my pressure, I could write out all my stress strain quantities quantitatively. So sig H, sig L, EH, EL. So we've got those values. So full stress and strain tensor. What's the rotation to get to the principal stress state? We are already in the principal stress state. What is the value of the principal stresses? Well, we know that basically sigma 1 equals sigma H, sigma 2 equals sigma L, sigma 3 is equal to 0. And if I want to find my maximum shear stresses, again, that's always going to be equals sigma 1 minus sigma 3 divided by 2. So it's just going to be my sigma L. Excellent. Let's look at the metal and the stress state below between the two rigid plates. So the rigid plates are rigid but well lubricated. I don't know why I had to say rigid twice. So let's see what's happening here. So I've got my coordinate system. I have, what is my material? it's a metal. So I have that green is my metal. So my Young's modulus is equal to, so I'm going to go ahead and clear my notebook. So I'm going to quit my kernel. So if I'm dealing with a metal, my Young's modulus is equal to approximately 100 gigapascals. My Poisson's ratio nu is equal to 0.3. We'll go ahead and get that. My stress tensor now, I do indeed, this is going to be my stress in the 2-2. This is going to be my stress in the 1-1. And then, let's see, I'm pushing, let's go ahead and actually, we'll write that down first. So I've got stress in the 2-2, I've got stress in the 1-1, and this is going to be a negative 85 because I'm in compression. All of my shear stress values are 0 because I'm well lubricated. Do I have a stress in the 3-3? Well, these are rigid plates and they're stuck. So when I push in this material with larger stress than here, I should expect my material to kind of pop out and expand in the 3-3 direction. So, but I'm constrained in the 3-3 direction by these plates. So I'm not going to have a strain in the 3-3, but I will indeed have a stress in the 3-3. And then, of course, I'm going to have a strain in the 1-1, strain in the 2-2, and then no strain otherwise. So that's it. We've got it. So let's go ahead and define our system. So let me constrain that. So my sig 1-1 equals minus 85 times 10 to the 3. My sig 2-2 equals 10 times 10 to the 3. And that's it. Pretty much all we've got. And we know that, E33 is equal to 0. Equals 0. So now I could solve for my 3 unknowns, 3 equations, because I need to solve for my sigma 1-1. Actually, excuse me. I need to solve for sigma 3-3, epsilon 1-1, epsilon 2-2. So solve my epsilon 1-1 equals 1 divided by y times sig 1-1 minus nu times sig 2-2 plus sig 3-3. And then repeat, repeat, repeat. We've done this exercise before. So let's do 2-2. This is going to be 2-2. This changes to 1-1. This is 3-3. This is 3-3. And this is 1-1. So I want to solve here. Oops. I think you have to close. Yeah, we need to close each of these. Close. Close. Close here. So I want to solve for E11, E22, sig 33. And makes sense. E11 is being pulled. E22 is actually, so my strain in the 2-2 direction, again, is positive. Because of that, again, strain in the 1-1 should definitely be negative because I'm pushing in, but when I'm pushing that other material expands, so 1-1 should be positive. And then sig 3-3 is negative because, again, it wants to expand into that direction, but it's being constrained. So we've got those values. So we got the full stress and strain tensors. We're already in the principal stress state. So this is my, basically we could see here, we have those 3 values. So my sig 1-1 would be basically my sig 1 would be sig 2-2, my sig 2 would be sig 3-3, and my sig 4 would be, actually, yep, exactly. And my sig 4, or sig 3, excuse me, sig 3 would be sig 1-1. So we are already in the principal stress state. So we have those, our 3 normal values are our principal stresses. So you can kind of rewrite that, actually. So my, basically, what I'm saying here is my sig 1 is equal to sig 2-2, my sig 2 is equal to sig 3-3, and my sig 3 is equal to sig 1-1. So we've got those values. What is the maximum shear? Again, tau max is just going to be equal to sig 1 minus sig 3 divided by 2. And then the rotation to get there, 45 degrees. If the rigid plates were not lubricated, write out the full stress and strain tensors and write out the equations that you that would allow you to calculate the components. Do not solve because you can't. So, looking at this problem, if I did not have any lubrication, I might have friction essentially between these 2 surfaces. So I could have basically a stress going in this direction, and I could have a stress going in this direction as well. So that stress, these stresses, again, their normal would be sig 3, but they're going in the 1 and 2. So I would have a stress sigma 3-2 and sigma 3-1. And I can calculate, the equation that I would utilize would be sigma 3-1 is equal to 1 over E times 1 plus nu times sigma, basically 3-1. and the same thing for 3, 2. So I just use those equations to solve for those values. That's it. So that would be included in there. Turns out that the metal we're working with is one of the formation alloys illustrated in the stress strain curves below in figure 3. These metals tend to yield when the maximum shear stress exceeds the yield stress. Which of the materials, if any? Ooh, that's a good problem. So my tau max again. So let's just say my sig 1 equals sig. Let's go over here. So we just said my sig 1 equals sig 2, 2. My sig 2 equals sig 3, 3. And my sig 3 equals sig 1, 1. So my tau max shear equals sig 1 minus sig 3 divided by 2. So that's my maximum shear stress. So let's go ahead and look and see if, so it says that the materials will tend to yield when the maximum shear stress exceeds the yield stress. So this is the maximum shear stress that my material will exhibit, and the yield stress of my material is, this is basically, and let's see which of these materials are going to yield. So here we see the yield stress for all of these essentially is going to be, this looks to be about like, this is 100. So like all of these are above 100 megapascals. So the only one that possibly will survive is the red curve, but I think we're still beyond, actually we're for sure beyond. What am I talking about? This is MPa, this is KPa. So all of those materials will not, I mean, again, the yield stress, or excuse me, the stress that's being exhibited here. So we exhibit, or we observe, or experience essentially a stress, or maximum shear stress of 47 kPa. The yield stress here is on the order of 50 to hundreds of MPa, megapascals. So none of these materials will yield. The stress is way too small. So none of those materials will yield. So hopefully that's clear. Sorry for my mispronunciation. Got too excited. So, all right, let's get into number 7. So look at the stress strain curves below. They've been basically created for new mystery proprietary alloy, cold rolled, annealed at these different temperatures and for the same amount of time. Explain the trend in yield strength. What strengthening mechanism is being employed here? What is the scaling? So if we are annealing, we know that we are changing essentially our dislocation density. So as our temperature and our time increase, our dislocation density decreases. And we know that our change in yield stress is proportional to dislocation density to the 1/2. So when I cold forge the material, I'm creating more dislocations. High dislocation density, 10 to the 14th per meter squared. But when I anneal it, it could drop down to as low as 10 to the 7th per meter squared. Number of dislocations per meter squared. So we see these yield strengths, again, follow this trend because we have this scaling here. So as you anneal your material longer, you're reducing the dislocation density, less dislocations, less impediment to dislocation motion, and thus a lower yield stress. If there's more dislocations, it's harder to move those dislocations because they interfere with one another, and so that's what's kind of happening here. So which was, again, that's kind of what's happening at an atomistic level. Which experiment has the largest concentration density of dislocations? Clearly the cold forged, right here, instead of the cold rolled. All right. Looking back at this, these stress strain curves, what could be explained in the yield strength difference between CR? Yield strength difference between CR. Just for information, this material can precipitant particle strengthen. The same. These are the same alloy, however. If the mechanism precipitant strengthening, how the critical radius? So, how can we explain the difference in yield strength between CR and basically some other materials? So, if we were to precipitate particle strengthen, we need, these are the exact same alloy. So, actually, excuse me, strength difference between CR. So again, there could be multiple differences. So if it's not essentially, if it's not annealing, we can be doing our other types of mechanisms. So one, we could be we could be doing solute strengthening, where our change in yield stress scales as C to the 1/2 concentration of solute. We can be we can also be grain size strengthening, where our change in yield strength CY scales as dg to the -1. We could also be precipitate or particle strengthening. Remember where we had our kind of curve here, and we're looking at our critical, so we go basically from here to here. We have kind of this critical radius here, where below here we want to cut small particles and we want to bow around large particles. Why? Cut small particles because we don't create as much surface area, bow around larger particles because we don't have as much curvature. So we've kind of seen that in the notes. So if we're looking at the previous stress strain curve, if we were looking at kind of differences in yield strength, it could also be any of these kind of properties going on. But if it's the same alloy, obviously then we're not kind of changing the solute, we're not precipitating anything, so it's probably grain size strengthening as well. So we could rank these in terms of grain size as well. So this would have the largest grain size, so DG would be the largest. This would be the smallest because, again, our change in yield strength is proportional. For grain size strengthening, is inversely proportional, up to 10 nanometers. All right. If the mechanism for cutting and bowing, if the volume fraction of the precipitate increases, also draw, so if we increase our fraction of our precipitates, so as we saw in class, so I have these fractions of particles. If I increase the number of particles, this critical radius is going to shift to the left. Why? Because as I kind of bring my line, compared to one that only has a couple particles, cutting now, I have to create way more surface area because there's more precipitates. So I'm going to shift over here. I want to cut even smaller particles because I don't want to essentially create that surface area. Draw how the yield stress will change as a function of grain size, include below 10 nanometers. So remember, we have this curve. We've seen this in class previously as well. So if I look at grain size, so initially as I kind of decrease my grain size, I shoot up, but then at 10 nanometers I go down. Why at 10 nanometers? Because now my grain size is so small that I can only fit like one dislocation in that grain. So I don't get that nice kind of dislocation pileup that causes the inner basically it disrupts that dislocation motion. So no dislocation pileup when you can only fit one dislocation in a grain. Great. This material can also exhibit various creep mechanisms at higher temperature and times. The three maps are all the same material in figure 5. So basically all the same material. So where are we at? What could be happening to explain the differences in the size of the regimes? Label all the regimes in the deformation mechanism maps. All right. So we know that this top one always occurs at 10 to the minus 1. That's my theoretical yield strain. Below there is my dislocation glide. And I could tell from these three maps that I'm going to call this 1, 2, 3. I know that my yield strength of 3 is greater than my yield strength of 2 is greater than my yield strength of 1. And so if I think of this as grain size strengthening, which possibly could occur, I know that my DG of 1 is greater than my DG of 2 is greater than my DG of 3. And let's see if that holds. So here I know the top is my power law creep. I also know this is elastic region, elastic. So this top is always PLC. And now I also know Nabarro Herring always exists more to the right. Nabarro Herring and Nabarro Herring. And I see I've got my Coble. So makes sense, right? DG is my largest my smallest grain size. So DG is the smallest grain size. Coble creep dominates because remember Coble creep scales as DG to the minus 3 versus this DG to the minus 2. Smaller grain size, more diffusive pathways, more diffusion along the grain boundary. That is going to kind of dominate. So my grain size of 3 is much less than the smallest, and so that's why we see that Coble region doesn't even exist in the first plot because the grain size is large. So that's what's happening with that system. Nice. So I'm working at Corning, and I'm running an ultrasonic test to measure the presence of microcracks in my glass. Whoever did this job for the glass purchased for the new library did a poor job because the glass fractured upon installation. The stress at fracture, so my stress at fracture was 100 megapascals. The Young's modulus for glass is 90 gigapascals, and my G sub C is equal to 2 joules per meter square. What was the critical crack size required for fracture? Well, I'm given G sub C, so I have to use my OR1 fracture definition, so it's equal to G sub C E over pi A. I'm given all those other parameters, so all we have to do is plug and chug. So Y glass is equal to 90 times 10 to the 9. My stress F glass is equal to 100 times 10 to the 6, and my 100 times 10 to the 6, and then my G sub C, GC is equal to 2. So I can go ahead and solve when, so sig, actually, stress glass set equal to square root of my Y glass times GC divided by, let's just put parentheses, I know we don't have to, I know I'm a crazy person, but pi times A, and solve, oops. Solve for A, come on, let's solve for A. So let's look at this numerically. So pretty small crack size is going to, so that is my critical crack size for fracture. So if I see a micro crack that's 5 micrometers, that is going to fracture. So that's the critical crack size required to fracture. Great. Now I'm working at Southwest and running the same ultrasonic test on the wings, but this time I'm concerned about fatigue. The wings are under 500 megapascal tensile stress during the flight, which is then unloaded upon landing. So basically, I've got a stress that looks like this. So 500 MPa and then unloaded 500, so et cetera, et cetera, et cetera. So that's how this stress profile looks like. The yield stress, so basically my sig max is going to be 500 times 10 to the 6. The yield stress in this material is 500 MPa, not important. My Young's modulus is now Young's for Southwest is equal to 130 times 10 to the 9. And then my fracture toughness of this alloy, so my K sub C is equal to 90 times 10 to the 6. For initial crack length, so my initial crack length A sub naught is equal to 1 times 10 to the minus 3. Will this plane able to undergo the typical 3, so my number of cycles to failure should be, NF ideal, should be 35,000. And then I'm given that my C is equal to 10 times 10 to the minus 10, and my M is equal to 4. Oops, I can't do this. It's my C. All right. So first things first, let's figure out what is my basically my fracture at failure. So what is my critical crack size at failure? So what I'm going to need to do, I'm going to need to go back to our notes. Oops. Let's go into our lecture 7. So let's go all the way down to fatigue. Let's go ahead and look at our equation. So we have our equation for figuring out what is our critical crack size at failure. So A sub C is equal to 1 divided by pi times basically my Kc divided by sig max square. So let's look at this. And we see here is A sub C greater than A naught. So my critical crack size is, or actually, yeah, that's great. So A naught. Okay, so A naught greater than A sub C. Okay, so we're fine. So we can continue on with analysis. So let's go ahead and just solve F and F. It's going to be equal to the following. So 1 divided by, let's do C times F is just a geometric factor. Delta sigma is just our sigma max. Because again, sigma delta x is because again, in this case, our we have a maximum stress of 500 megapascals. Our minimum is 0, so that's our delta sigma is also sigma max minus sigma min. So sigma max times pi over times square root of pi, and then this is going to be to the m power. So let's do all that, and then we're going to multiply everything here times basically A sub C to the 1 minus m divided by 2 power minus A naught to the 1 minus m divided by 2 power, and we're going to divide all that good stuff divided by 1 minus m divided by 2, and we need actually C, little c. And number of cycles to failure is going to be 1,463. So cancel that flight, Southwest. Please, please, please. So that's it. So hopefully this has been helpful. Again, review this before your exam coming up soon. And If you have any questions or if you would like some more additional problems, please let me know. Thanks. See you next time. Bye.